Alright, welcome to the first extension for Chapter 4 of Math 9. This video is actually going to be pretty long. It's jam-packed with lots of information. Stuff that you actually really need to know to be successful in your senior years of math. So, yes, there's a lot, but I hope you can learn this and learn this well, because if you do, it'll set you up for success later on down the road. Okay? What I want to do, first of all, is just tell you some definitions here of a few words that we use in math. A set really is the following. It's a collection of different objects. Okay? So if I ever ask you, here's a set of things, it's just a whole bunch of different objects put together. Now, an element of a set is really one of the objects, one object in the set. Where a relation, and this is the key word, we're going to see this a lot today, a relation really associates, so it makes a connection, or it associates elements of one set with elements of another set. And we're going to look at relations today, and they can be represented in many different ways. As words, something called an ordered pair, which you might have seen already before when you do graphing. In a table, like a table of values, or as an arrow diagram. And those are just to name a few, but those are the ones that most often are seen in math. So let's look at this example here. I've given you a set of Canadian coins, yes, and the images on them. You might not actually see the penny anymore, but yes, it was out there before. So as an example with this penny, I can say the element of the first set. Well, really what I'm saying is, how do we relate this? So, an example of an association of the value of the coin to the image on the front. So in this case, for the penny, I'll say the value is 1 cent has the image of what's on the front? Ah, yes, the maple leaf. So that's an example of an association of the value of the coin to the actual picture. So I can list the above relations using actually ordered pairs. So for example, I said the penny, right? So 1 cent. And then I'll say maple leaf. If I look at the nickel, that's what? 5 cents, right? 5 cents. That's the beaver. If I look at the 10 cents, here again, remember the first value is always the amount of how much it's worth. And then the next thing, or the next element, is the actual picture. That's the boat, which is called the blue nose. And then the next one, yep, I'm just going to list them out, right? 25 cents, or a quarter. That would be then the moose. Don't know if you've seen the 50-cent one before, but that is a coin that is produced, not really in circulation. That picture actually is called the coat of arms. Those of you who are taking social studies, talk to your social studies teacher to figure out what that's all about. And then we have the loonie, which is $1. And that's, of course, the loon. And then finally, we also have $2, which is the toonie, but it's actually the polar bear. So here, then, is an example of me connecting the above relation using ordered pairs. Now, of course, I can translate to a table as well. It's really just translating those ordered pairs into a table image. So the coin value of 1 cent was the maple leaf. I'm just going to write this as ML. Okay, I'm just trying to speed this up. Coin value of 5 cents, that's the beaver, B. 10 cents, the blue nose. I guess I should say beaver. I can write that out. I have to because they both begin with B. 25 cents, the moose. 50 cents, the coat of arms, C-O-A. The $1, I can write down loon. And the $2 polar bear, P-B. Not peanut butter, but polar bear. Now, as an arrow diagram, how does it look like? Well, one of the sets will represent the coin value, and the other set will represent the actual image or picture on the coin. And how is this associated? Well, the coin value, I'll say this, has the picture of and then I can state the actual image. So for example, the penny, the 1 cent, has a picture of the maple leaf. So they connect that way, right? Whereas the 5 cents has the picture of the beaver. So they connect. 10 cents has the picture of the blue nose. And then I draw an arrow to connect them. 25 cents, moose. 50 cents, the coat of arms. And then finally, the dollar, of course, is the loon. And $2 is the polar bear. So this is just another way of showing the relationship or the relation between the coin value and the image. Okay? Now, I wanted to say something before we do part D. Note, it says here, it says since each element in the first set only matches with one element in the second set, this relation is called a function. So there's a special word when there's a one-to-one relationship like this. We call it a function. All right? And in words, what do we actually just do with these previous examples? Well, we're showing a relationship. So I'll say the relation shows the association. Okay, the key thing is the association, right? The connection of what? Of the value of the coin. That's the first part, right? Value of the coin to the picture or the image on the coin. And that's how we can describe this with words. All right? So turning the page now, let's see if you can look at example number 2. Oh, look at this. A typical Burnaby South honor students can get homework assigned from all their academic courses. Yes. And the subject area can be associated with the mean number of homework questions. Means not just like, oh, I'm really angry, but really in math it's the average, okay? It's the average number of homework questions assigned. So consider the relation represented by the graph below here. And I want you to represent this relation as an ordered pair. So notice we have subjects, and then we also have the number of questions. So for example, if I have English as my subject, how many questions? Yeah, 5. Then I get math. Whoa, those math teachers are really, really, really mean, hey? 20 questions for you to do. Science teachers, oh, they can only give 10. The social studies teacher, well, they give us 5. And then the French honors teacher gives us, what is that, maybe 8. So there is an example of your ordered pair. Once again, the subject, since it's on the horizontal axis, is the first element. And then the y-axis, the number of questions, becomes your second element. As a table, now it says list in alphabetical order. So if I have to do this in alphabetical order, I have to rearrange this in alphabetical order. English first, which is 5 questions. And then what? A, B, C, D, E, F, G, H, I, J, K. Oh, don't forget French, right? French. E, F, G, H, I, J, K, L, M, M. Math is next. And then science. And then socials. Okay, they don't always have to be in order, but sometimes it's nice when you do that. It's just easier to find things. That's all. How about as an arrow diagram? This time, list the numbers in, well, list the words in alphabetical order, okay, and list the numbers in numerical order. So remember, we have subject, and we have number, right? Number of questions. And what is the connection here? The subject, so English, I'll say, gives on average, and the number of questions. So let's list them out. English, French, math, science, socials. Okay, and then it says list the numbers in numerical order. So 5, 8, 10, 20, and then do we have to write 5 again? No, we just need to write it once. Okay, that's an element in the set. We don't have to write the element twice. What we'll find though is, yes, English goes to 5. French, yes, goes to 8. math goes to 20, science goes to 10, and then socials also goes back to 5. Okay? And that's how you can represent this as an arrow diagram. Alright? Now, the next curious thing is, well, what happens when there are so many ordered pairs in a relation that is, it's impossible to list them all out or represent them in a table? Well, looking at this example, the places in Burnaby that are within 30-minute walking distance of other places in Burnaby. And by the way, note, I never said those things had to be different. Both sets in the relation actually can be the same. So how would we describe this in words? Well, I'll say this relation associates what? Yeah, places in Burnaby that are within 30 minutes walking distance, what? To other places in Burnaby. Okay? So really thinking about locations in Burnaby, that if I choose 2 of them, I can get to them from one within 30 minutes. So what's an example of that? It says list 2 ordered pairs. So perhaps I'll say something like, perhaps I'll say something like this. I'll say, how about Burnaby South? That's where we're going to start. And where am I going to end? Maybe at the SkyTrain station, the Royal Oak SkyTrain station. Can't spell SkyTrain. SkyTrain station. Why does this work? Because both are places in Burnaby, and I can get to one from the other within 30 minutes. What's another one? Oh, maybe it's, yeah, Metrotown. Sure. Metrotown Mall. And where would I go after that? Oh, maybe the Bonzer Recreation Center. Okay, those are both places in Burnaby, and I can get there within 30 minutes. Alright, and you might have some more examples, but those are the 2 I have chosen. How are we feeling so far? So far so good? Great, because now I want to give you some more definitions now. Okay? Now, there is a new term that we're going to introduce that represents the set of the first elements in a relation. Okay, so that's like the first part in an ordered pair before the comma. We call that the domain of the relation. Now the set of second elements, so that's the one after the comma, that is called the range. Okay, so I think in the previous one, remember how I had like 1 cent versus maple leaf? Remember that? So that 1 cent would be the element in the first group, so that would be a domain. And then the range example would be the maple leaf. Okay? So really here, I've got another definition I need, and we've seen this word before, but I'm going to write it again now. A function is really a special relation where, and this is the key thing, each element in the domain is associated with only one element in the range. Alright? Star this. You'll see these terms a lot in grade 10, 11, and 12. Domain and range. So, let's get some practice with now domain and range. I like you to state the domain and the range and then decide if they are functions. Remember, functions, each element in the domain is associated with only one in the range. So let's see the domain here. That would be the first set. I'm just going to abbreviate this. Afghan hound, AH. Chihuahua, CH. A corgi, CO. Golden retriever. I think these are all dogs, right? German shepherd. And a Malamute, M. Where the range is the heights, so that's 20 centimeters, 30, 60, 65, 75. Now the question is this a function? For each element in the first set, is it only connected to one element in the second? And the answer is yes. I know you're thinking, look, they both go there, but that's okay. They're still only connected to one element. So I'll say, yes, it is a function. Each element in the domain is associated with, and this is the key word, only one element in the range. Okay? Alright, I'm going to ask you now to try B, then C, and D yourself. And then once you're done, double check your answer with mine, and then we'll review together. Okay, so press pause and get to work. Press pause. I think listing domain and range is pretty straightforward. Key part here, is this a function? And I'm going to say, look at what happened with Apple. There are actually two elements it's connected to. That's bad news. Therefore, it's not a function. Apple is associated with two elements in the range. That's no good. So it's not a function. Okay. Remember, we don't have to list things twice. Okay. It's nice to also list things in order. In this case, is it a function? Look here, 1, 5, 1, -1. So the 1 actually then spread over to two values here. That's a problem. That's not the only one, right? Look, 2 went to 7, but also 2 goes to... So once again, function? No. This one's interesting. You might have thought the domain is the number of hours worked, so 0, 1, 2, and so on. You need to understand that these are only whole numbers, so maybe we should use this saying that the number of hours worked, H, or hours, has to be a whole number. Remember that W symbol we use to represent whole numbers? This means belongs to the set of whole numbers. This is like a sideways E thing. Okay, so the hours for the domain have to be whole numbers. And then the range, well, if you're going to pay $8 per hour, either 0, 8, 16, so forth. So it has to be actually multiples of 8. And is this a function? You bet, because for each hour worked, you can only get one number or one payment amount. Okay. Now, in a workplace, though, just want to let you know, a person's gross pay, meaning the pay before taxes, often depends upon the number of hours worked. This is why sometimes the gross pay is called the dependent variable. Dependent variable. Right? Often depends. While the number of hours of work, which is, I guess, what you can choose, is the independent variable. Okay. Now on the next page, I'm going to try to connect this idea of independent and dependent variable. So here's a picture of what a function is all about. So imagine this as my function. Okay. You're going to start with the independent variable. Whoa, what's happened there? Independent variable. Or that's what they call the input. And when you put it into the function, what do you get? Yeah, the output. Or the dependent variable. So let's look at this example here. Joe, he works at Superstore. He earns $7.50 per hour. Employees are actually paid for each hour worked, so there's no part hours. Let H be the number of hours and D the dollars earned. Make up a table of values of up to 4 hours. So you need to know our independent variable, which would be hours, and our dependent would be the dollars earned. So 0, that's right, nothing. 1, $7.50. 2, $15. 3, $22.50. 4, $30. Okay. So there's a table of values. Yay! Now what's my independent variable? Yeah, that is what you can choose, the number of hours worked. The dependent, what they provide you, which would be the actual dollars made. Now how about if I ask you to write the domain? Well, once again, my domain here is just the set of elements in the first set. 0, 1, 2, 3, 4. That's it. Actually, it could be more, right? So I should go further. Where, of course, n represents a whole number. My range, yeah, that's like every multiple of 750. Or I'll say 750 times n, where of course n still has to be a whole number. Okay. And so my question now is, can we graph out the function? Well, of course we can. I'm going to draw my axes here. We know our independent variable is hours. Our dependent variable is the dollars earned. We have to pick a nice scale. I'll just use 2 dashes for every hour because I think I have enough space here. You can do something different if you want. And then I think I'm going to use, I think I'm going to use maybe 4. 1, 2, 3, 4. That's $10. 15, 20, 25, 30. Yeah, let's just do that. Okay. And I want you to graph out the function. So notice if I make, or I don't work, I make nothing. If I do 1, it's $7.50. If I do 2 hours, it's $15. If I do 3 hours, it's $20 to $50. If I do 4 hours, it's $30, and so on. Okay. Now, should I actually connect the dots here? Because if I connect the dots, what I'm saying is if I work like half an hour, I still get paid for half an hour. And that's not the case because no part hours are paid. So I'm going to put a note here. Please do not connect the dots in this case. Why? Because you can only work a whole number of hours and also get paid for that too. Okay. Now, is this relation a function? Remember, for each value of the independent, it's only connected to one value of the dependent. And the answer is, yeah, it is. Because for each element in the domain, there is, and what's the key thing? That's right, the words only one connected element in the range. Okay, so once again, this definitely is a function. Now, can you write a mathematical equation to describe this relationship? So if I asked you for D for dollars earned, D for dollars earned, how does that equal to N, the number of hours worked? And if you said 750 N, that'd be correct, where of course D equals to the dollars earned, and N equals the number of hours worked. Nice. Okay. Like I said, we've done a lot. There's a lot in this video. But here's another crucial part I need to know. Now, an equation is really just the relationship between the input and the output. This above particular equation, this d equals 750n, with two variables, is a function, and thus can be written in something called function notation. So to change the equation into function notation, we do the following. Instead of just saying d, the dependent variable, we have to tell it what's it dependent upon. So we write this like the following. We put d with a bracket n. This is said d of n. Okay? Do not mistake this. This is not d times n. Okay? This whole notation here is called d of n. The dollar amount is dependent upon the number of hours worked. And that is equal to, and the right hand side stays the same, 750n. This whole expression here is function notation. And by the way, if there's no context to the problem, so I use d because I talked about dollars, if there's no context to it, then a lot of times in math we use this f of x, or they sometimes use the notation y of x. Okay, like y is the dependent variable, it's connected with the independent variable x. Okay, so get used to this idea of function notation too. That appears quite a bit in senior level of math. So to help you solidify this concept, and I know this is the last page, so thankfully you're almost at the end. For the equation y equals to negative 3x plus 5, rewrite using function notation. So a lot of times y can be written as function notation, just write that as f of x. Okay, so I'm really just saying this y gets transformed into this new notation f of x. F of x means the function with respect to x, and that's why on the right hand side we have x. So if I give you something like part b, what's this f of negative 1? What does that represent? This means find the actual y value when x equals negative 1. Or, in my function notation, I'm replacing the x with negative 1. So that means on the right hand side, I'm also replacing the x with negative 1. And then evaluate. What's negative 3 times negative 1? That's positive 3 plus 5. The answer here is 8. So really what I'm saying is when x equals to negative 1, the y value, which is this function, is 8. So with part C, if I said then determine x when f of x equals to 14, really what I'm saying is find x when the y value, or the function value, is equal to 14. So once again, using my function notation equation, I want us to now replace f of x with, correct, 14. Oops. And now go ahead and solve. Subtract 5 on both sides. Divide by negative 3, and you get the x value being equal to 3. Okay? A very key example to understand function notation. Okay, I have one more here to finish off. Let me apply this to something in real life. So, sunscreen. You know, you've been in the summertime, you wore sunscreen a lot, I hope, so that you won't get skin cancer. I don't know if you've seen other bottles, but there are these things called protection factors. SPF, sun protection factor. Usually you see these numbers. You rarely see these because the SPF factor really represents the percentage of the sun's UV light that passes through a sunscreen. Okay, you don't want to have sun protection factor of 2, because 100 divided by 2 means 50% of the sun's rays pass through your skin. That's pretty bad. And that's why most people only buy SPF like 30 or 45 now. Okay? So if I ask you to change this equation to function notation, really I'm saying is, can you write P as a function of something else? So the protection factor P is a function of what? Yeah, of S. So we just go P of S. And that's the only change to make this equation written in function notation. Part B says, find the percent of UV light that passes through each sunscreen factor. So really what I want you to do now is do this. Find P of 2. Find P of 4. Find P of 8. Find P of 15. And once again, you'll hopefully see why we don't use those P of 8s and P of 15s, because a lot of the sun gets through. So in any case, that would be, of course, 100 divided by 2. That means 50% of it goes through. 100 divided by 4, that's still 25%. That's pretty bad. 100 divided by 8, that's 12.5%. That's getting better. 100 divided by 15. Ooh, what's that? I don't even know what that decimal is. I think it's about 8.33. Oh no, 6%. That's much better, right? 6.7%. Still maybe not so great. Oh, this is 4%. That's better. 100 divided by 30. That's what? Even better. That's only 3.3%. 3.3%. I guess the best yet would be P of 45. So 100 divided by 45. That's almost what? Almost 2%. So not bad at all. 2.2% of the sun's light passes through. Now, if I want to avoid getting skin cancer and want to ensure that 95% of the sun's UV rays will not penetrate my skin, what is the minimum SPF factor sunscreen that I need to buy? So if I want 95% of the sun's rays to not penetrate, that means I am willing to allow 5% of it to go through. So really what I'm saying now is, using the formula P of S equals to 100 over S, I'm okay with this P of S here being equal to 5, right? So 5 equals to 100 divided by S. We can cross multiply. 5S equals to 100. So S equals to 20. So the minimum SPF factor that I will buy is 20. Anything bigger than 20, I'm happy, because I'm okay with having 5% of those sun rays penetrate my skin. Alright, that's it for extension number 1. Like I said, lots of material here, but very important to set you up for success in the future.